essential question and learning target is a little different for this part of the lesson. So the essential question is, how is the combined gas law used to solve a variety of gas law problems? And then the learning target is, in this lesson, you're going to learn how to use the combined gas law to solve any of the individual gas law problems, like Boyle's, Charles, or Gay-Lussac's. So we now have the last of the gas laws that we're going to learn, 6 of them. How are we going to remember them all? Well, the good news is that we don't have to. As we learned in the previous lesson, the combined gas law is derived from the ideal gas law. And the difference between the two is the ideal gas law is one set of conditions, where the combined gas law is 2 sets of conditions, a before and an after, in a closed container. So we know we have a combined gas law problem if there are 2 sets of conditions, ones and twos, befores and afters, in the same closed container. What if temperature is constant too? We simply cancel the t's, because those numbers will be the same on both sides of the equal sign. So what do we have? We end up with what we learned originally was Boyle's law. And I don't expect you to know the name of the law, but you should know that we started with the combined gas law, canceled the t's because they were constant. And so what we're assuming here is that we have the same closed container, 2 sets of conditions, and constant temperature. According to this problem, we have the combined gas law again, because there are 2 sets of conditions in the same closed container. So we don't see N. And if the pressure doesn't change either, we simply cancel the P's. So before we even start the problem, cancel the P's, and what we're left with is Charles' law. So again, we started with the combined gas law because we have 2 sets of conditions, and then we canceled pressure since it remained constant. So what we end up with is V1 over T1 is equal to V2 over T2. Same closed container, 2 sets of conditions, constant pressure. All right, finally, I think you're probably getting the picture here, but what if volume doesn't change? What if it's constant? You got it. We're going to cancel the V's, and what we end up with then is Gay-Lussac's law. So Gay-Lussac's law starts with the combined gas law. We know it's the same closed container, a before and after condition, and constant volume. So before we even start the problem, we can cancel volume. All right, so to sum up, the ideal gas law is used when there's only one set of conditions for each variable. We don't see any ones or twos here. The other tip-off that the ideal gas law is being used is that the ideal gas law contains moles. And when we compare that to the combined gas law, moles are not included. So when we see moles and pressure and temperature along with volume, we know it's the ideal gas law. The combined gas law comes from rearranging the gas law to solve for P, V, and T. When the conditions are in a closed container, hence no N, and the conditions are changing. So we have the before and the after. So if a variable isn't mentioned in the problem, or the problem states that one of the variables is constant, all we have to do is to cross that variable out of the combined gas law. So here's the combined gas law, and by simply either canceling out pressure or volume or temperature, if those remain constant, all of a sudden we're down to two gas laws to remember. So PIV-NERT, PV equals nRT, and the combined gas law, P1V1 over T1 is equal to P2V2 over T2.